that is just unheard of. But it's not ours, it's not Canada's. It's on the border. But I've never seen Niagara Falls. I think I'd like to see it if I die. I've never seen the Grand Canyon. I'd like to see it if I die too. Those are the two things that are my took that gold to do. Alright. I got another picture, I believe. Yeah. This is from the side, that's looking right dead at it. All this came off the internet. Don't look quite so touching that way, doesn't it? Here we go. That should be in red. The word biologist. So that's a blank on yours. Alright, let me go ahead and make it red here then. I didn't pick that up apparently. Any other problems y'all see?
Liquid.
Alright, good. You do know what a biologist is, right? Anybody who studies what?
Biology.
Life.
Liquid.
The study of life is biology. Study of living things is biology. And you got the branches, some folks just like to study spiders, and some folks like to study ecology, and they have the branches. But it all boils down to biology, which is what this class is about.
Liquid should be red at the bottom.
Liquid should be red? All right. Well, I tell y'all that, water is the key. It is the key, and that's why. You need something, a medium to transport. If our highways and our truckers were to shut down, how long would life last in the United States?
No.
We run on our trucks. Railroads used to be, but our truckers, there's the strength. If they go on strike, you will feel it fast. In our body, the highways and the byways are your blood system. Everything is carried around your body through the blood, which is mainly water. And even in your cells, those organelles are floating in cytoplasm, which is mainly water. The stuff that flows by your cells, we call lymph, which makes that little blister. The water is a blister. That's mainly water. Just can't get away from it. You cannot dissociate water and life. They come hand in hand. And that's why we study. There's a branch of science that I have had. It's called limnology. And I loved it. It's the study of freshwater ponds. I like to fish. So I took that class at some mistake. And I learned about where you might find fish on certain days because of the nature of the animal. So when I go fishing now, I have a better idea where I want to put that boat, on what time of the day where the sun is. I used to just fish, but now I have a method I'm using, and I think like Bill Dance and the Good Fishermen, they know that method. They know where to go to find it, and that's what I have learned over time. Okay, so. But the first line tells you, if I said, write me a paragraph on what is life, it may be hard to do. I mean, you can beat around the bush and never actually get an animal come out of the bush. It's just hard to say. And I've been doing this 35 years, and I know a lot of things that make life possible. Maybe all together that is life. But I don't know if I could write a good paper on what is life. Some folks know something, they just can't explain it. It's like trying to explain to your child how to tie the shoe. It's better to say, watch me do this for you, and try to put it in writing and say, about the rabbit ran on her stomach and dove in the hole, that kind of stuff. Have y'all heard that thing?
Yes.
I never used that. I just said, do what Daddy did.
Put on that one swing.
And, I cannot tie my son's tie unless I'm behind him reaching over his shoulder.
Yeah.
My wife can tie from the front. I got to get behind my two little boys when they're growing up, going to church, and he's 4 years old. And a tie is easy to tie. But I got to get behind and reach over him. Kind of tie on me that way. That's how I learned it. I don't believe I could just day tie a tie looking at you. I might make a hanging loose. I tell you about the blood being mainly water. I mean, it's 92%. 92% of the plasma is water. But the plasma, in the plasma is floating your blood cells, floating the platelets, floating the proteins, the food's floating there, your medications you've taken are floating there. That's your transit system, your blood. And plasma, you know, in the old days they used to use rivers to float logs down to the sawmill, right? Well, at that time, the river would be the plasma, the log would be the red blood cell floating in the river. And you can't say much more about that than that. And like I tell you before, dehydration, it's a really bad condition. You lose that water, you're in really bad trouble. I tell you earlier, if you ever get yourself stranded somewhere and can't find your way home, you better find water first. That's what's going to kill you first, water. Food, the water, the lack of. I found me a picture. That's blood that's been spun in a centrifuge. Now you shake it up, guess what color it turns? All red. But when you spin it, the red stuff at the bottom, that's your blood cells. They're heavy. They spin to the bottom. And see that little clear layer between the yellow and the red? That's called the buffy coat. That's where you find the white blood cells and platelets. And the yellow on top, that's the plasma. That's the plasma.
You said bucket coat?
It's called a buffy coat. Buffy layer. Buffy. Now that's not my term, that's what we call it, the buffy layer. And in that layer there's your white blood cells. That's why it's white looking right there. But the red blood cells, good God, you have many red blood cells. If you took a drop of blood, that's too big. If you took a dime and put between your fingers and squeeze real hard, the space between your fingers is about 1 millimeter. The dime takes up 1 millimeter. If you had a square piece of, like a dice, set of dice, and all that thick all around, would that be small? Extremely small, wouldn't it? How do you put dots on that one? Anyway. But the fact is, in that little bitty area, there's 5 million red blood cells. How small are those rascals, you reckon?
Tiny.
If you can put 5 million, take that dime and squeeze it hard, and then the gap between your fingers where the dime is, that's 1 millimeter. If I had a sugar cube that was 1 millimeter all around, you probably wouldn't even taste the thing. It'd be so little bitty. And in that same area, there's 5 million red blood cells. I mean, they are little. And in that same area, there's around 5,200 white blood cells. They're bigger. And the platelets, they're about 350,000 platelets. They're just there to make your blood clot. And when you get cut and you want the blood clot, the platelets do that for you. The white blood cells, most folks say they're fighting disease. And that's right, that's not all. There are 5 kinds of white blood cells in your body, not one kind. 2 of them are fighting disease. Other 3 are not. One of them, you ever seen like in high school, 2 guys getting in a fight and other guys go, hit him. They're egging it on. Mm-hmm. Well, one kind of blood cells are egger owners. They make the other blood cells fight faster. They're the cheerleaders. And then you got another kind of white blood cell. His whole job is to give you your allergy. You produce your own. If you're allergic to cat dander, You do it to yourself.
IgE.
Those white blood cells, which they also fight internal parasites like worms and food you don't cook well. A lot of them you'll kill.
Yeah.
The trichina worm you won't kill. That trichina worm is in like pork.
Yeah.
And I always tell you, cook pork black.
Don't eat.
If you buy pork from Winn-Dixie and Kroger and Walmart and Sam's Club, supposedly that's been inspected. Stamped. Yeah, stamped. Well, there had to be scandal a while back about that. When you buy that stuff there, it's been stamped to be clear. So if I want to go outside and cook my steak medium rare, then I can be safe that there's nothing in there that I got to kill. Now, if I go shoot a deer in the woods, and I do that, I cook that meat well done. Now, no one expected that meat to say it's good. I cook deer meat, well, I say well. But if I go to Winn-Dixie and buy it, and I don't even look anymore because the law says they got to, I assume. But about maybe 15 years ago, there's an FDA inspectors who are getting paid under the table. Just stamp the food and don't look at it. What's wrong with that?
It spreads disease.
Dangerous.
There's no protection. Oh man, they hit the fan, buddy, and folks got scared to buy food, even Stanford didn't know. So they really put, those guys have put under the jail. And I guess now I do trust them again. That when I buy meat from Winn-Dixie or Kroger or wherever, that it had been inspected. And I can cook it to, just slightly warm. Some folks, I like my meat cooked a little better than that. But my brother-in-law, he likes it almost out of the animal. just warm it up, please.
He licks it.
And it's still red, and I go, yeah. But now I have ordered food like, go to Outback, and I want mine medium. It comes in not quite done, a little red inside, and it's got a good taste. I can't describe it, but a lot of folks, it's up here. I don't want to see that red. And now chicken is not, chicken you got to watch out for too. Chicken spoils over time. And that's why a lot of folks are vegetarians. They want food with meat. It ain't worth
What's
food
the
with
one
it.
that
You ever had food poisoning?
Yeah.
Had it one time. You wish you were dead. It is so bad. All right. Anyway, that is a sample of blood that's been drawn and spun in a centrifuge to make the parts separate. Now, if you shake it up, it's going to be all red, just like it was when it got drawn in the first place. All right.
The first part is one.
Now, thank God water is so abundant because it's so needed. But there's nothing here you don't know yet. I'm reteaching. I'm trying to stress a point. I mean, water has properties that uniquely make it suitable for life. And like I said, before I go, I need to once again explain those properties. And one of them is that it's always made of two hydrogens and one oxygen. Now, it's a covalent bond that forms a molecule. That one water molecule, those H's are hooked to O with a covalent bond. But now, this molecule, what holds those two together? That's a hydrogen bond. Now, give me right now. Here's a molecule. These two fingers are hydrogen, and my thumb is oxygen. These are all hooked together with covalent bonds. Here's another molecule. Now, what hooks these two together? This hydrogen is attracted to this oxygen with a hydrogen bond. Therefore, they stay together. All right? But the actual unit itself, these are covalent bonds. These are covalent bonds. But what makes, now, will this finger and that finger stick together? No. Those hydrogen, they're going to fly apart. How about the two thumbs? They don't like, but it's going to be like, this is going to be the bond. Now, is trying to fly apart, is trying to get, but that holds it real firm. The fact that the hydrogen bonds, you see right here, are pulling together, and these bonds are pushing apart, that really makes this a really firm arrangement. There's no movement in there.
So from the one single hydrogen to the oxygen is
That's your hydrogen bond.
hydrogen bond.
But within the entire molecule, what's making that work are all covalent bonds. Because they're all sharing. They're sharing. They're not ions. Because, see, ions dissolve in water. If water was ionicity, it wouldn't work. But water can break apart, can break salt, your table salt, that's an ionic compound. You put it in water, water breaks it apart. So I got sodium, I got calcium, I got chlorine here. That's another way to look at it, and there's nothing different you saw. Last time I showed you a bunch of the red dots. But obviously, around the H's is your plus area, and around the O is your negative area. That's a molecule of water. All those are joined by covalent bonds. But what joins that to the next water molecule is when his H is drawn to that O. That's your hydrogen bond. And the same token, though, the other H is repelled by that H. So I got to be pulled together and pushed apart, and that locks them down. You know, it ain't like a necklace. They're locked. They're like welded. If you took a chain and welded links together, then you couldn't move them, could you? But that's how that works. And then to me, do you see Mickey Mouse again? The ears. Every time I see it, I think of Mickey Mouse. Or the Mighty Mouse. They still got those stupid little ears up there. You just turn sideways. I'm gonna look ahead just a minute. I wish I had my other picture with the dots all over on this slide here. I might one day put that on. I showed you in the last slide, the little red dots around the oxygen.
Yeah.
And not many dots around the hydrogen.
Mm-hmm.
I need that picture again right here to show you again. I mean, you get done copying, then read it. Right now, you're kind of like tracing, you're not looking at anything, you're just getting a word there. But now, if you read that, it's going to tell you what I've been telling you before. Hydrogen loves electrons. He is a hog. He has 6. He needs 2 more. He's begging for 2 more. He wants them bad. Now, there's hydrogen out there. He can kind of tear that. He has a low electronegativity. The picture I showed you yesterday had the O with all the red dots all over it. Then H and H are just a few red dots. That picture is showing you what I'm telling you right here. I wish I had a picture of my slideshow. I'm going to probably put it on there. But the oxygen has a lot more red dots, electrons around it, than the hydrogens have. That makes him real negative up here around the oxygen. And there are a few electrons, but they can't overcome the positivity of the hydrogen. So around the oxygen, well, I can go back and show you. Around the oxygen here, where you have tons of electrons, that's your negative field. And around the H's, where you don't have many electrons, that's your positive field. And you're gonna find that the green of this one is drawn to the blue of the next one. But the blue of this one does not like the blue of the next one. And the green of this one doesn't like the green of the next one. Same don't like each other. Difference do. And that's van der Waals force working there. But if I think I want to go back to another slide so I get that slide. I like it because it needs to be right here probably. But the fact of the matter is, if the electrons were shared equally, it wouldn't be polar then. It'd be non-polar. It wouldn't have an area where there's all the negative and all positive. The fact that they're not shared equally is the beauty of water. Because it's not shared equally. That makes water work. Now here's the result, and I just told you this. And I'm telling you again what I just told you. Now right now, put your blinders on, just fill the blanks in without reading it. Then go back and read it and see what it says. If you trace a picture, that's a problem. You're tracing, but you're not actually looking. Here, when you put the blanks in, you just kind of slapping down, but you're not reading. You're just trying to find those blanks. Then go back and read it. It should make sense because I do see I forgot the H and the hydrogen. I forgot to hit it. I'm not worried about it right now. You can see the hydrogen. I've got the N2 and the oxygen. Now, if you've written it, let's go back and see what it is about. Now, I'll tell you four. Around the oxygen, what kind of field is that? Positive or negative? Around the oxygen, what is it?
Negative.
It's negative. How about the hydrogen? Positive. Now, when you have those differences, that's called polar. If you didn't see any difference and they're all kind of the same, we call that nonpolar. But this definitely is polar because one of the atoms is full of electrons, making it negative, and the other atoms don't have many electrons, therefore they get to remain positive. Well, that's the beauty of water. Water is a polar covalent compound because they don't share the electrons equally. Oxygen is the hog; he gets all of them. Therefore, that side turns negative. But that's why water works. And it might not seem important right now, but it's the fact that the way that those two interact, that gives them the uniqueness of water. Is the way they are held together like that. There's nothing like that we know of. Water. And you know also, water, if you put water in a glass jar in December, put it on your porch, and the glass jar freezes, and then it busts. Why will it bust? I thought things got smaller and smaller and smaller. Why will it bust? It expands. Nothing does that. Water, if you're on a centigrade scale, at what temperature water freeze? What number is it? On centigrade, not Fahrenheit. Fahrenheit 32. Zero. If you have two thermometers and one says 32 Fahrenheit, one says 0, same temperature. You're freezing. On Fahrenheit, that's a man. Fahrenheit's a man. Name for him. Celsius is a man. On the Fahrenheit scale, 32 is just as cold as 0 over here. Don't let the numbers fool you. This 0 is no colder than that 32. It's the way the scales are made. As far as now, what water does on the Celsius scale, it will get smaller and smaller and smaller, fill in more areas, and at 4 degrees, it expands. And as it expands, it hardens to ice. That's what breaks the ice. That's what breaks the car motor. Antifreeze prevents that from happening in your car. Because even that big old motor in your car, inside there, there's water right from your radiator. If you don't put antifreeze in there, that water's going to get smaller, smaller, fill up more of the nutrient cramp in your motor, and all of a sudden it's going to expand, which will power you and imagine, and crack that motor block. Next thing you know, you got to buy a new motor. Because you didn't protect it for the wintertime. Most of your milk jug, my mama, we lived on the river growing up, and she'd buy like 4 gallons of milk at one time, and she'd freeze 3 of them. And she didn't use glass, of course, she used a milk carton, and it would expand, but not hurt the carton at all. And that way it avoided trips back to town. And back then, gas cost a whopping 23 cents a gallon. We couldn't afford that kind of gas. Oh, Lord. You think about that now? I could buy a gallon for less than a quarter. Y'all remember those days?
Yeah.
Only folks my age can remember those days. And when he had 50 cents, my dad said, I ain't buying no more gas. It's getting too expensive. Now it's what, $3.50? He's still buying gas. All right. Oh, for the good old days. Anyway, the fact that water is a polar covalent compound and how the negatives form around the oxygen and the plus around the hydrogen, that makes water in a class by itself. Nothing like water. Okay? This is another look. Now, in my picture up there, how many molecules can you count in water in that substance?
11.
I count 11. I'm counting the red dots.
11.
I'm counting the red dots. But I'm going to look at the oxygen, because that's going to be the water. I got 11 of them. Now, what's making that not just fall apart?
Hydrogen bond.
Not the covalent bonds.
Hydrogen
The
bond.
hydrogen bonds. You see right here? There's one of them. There's one of them. What's happening here, though?
Repel.
They're repelling each other.
Yeah. Here, what's happening here? There's an attraction. There's an attraction. What's happening here? Repelling. Why won't just like that? Because it'd be repelled. It won't just wad up like a piece of paper because it'd be repelled too, right? And what for the repulsion, it would just wad up like a piece of paper. And what good would that be? Not at all. The fact that there's some repulsion going on, it won't wad up. It stays this shape right here. And anywhere you find there's a repulsion going on, but there's an attraction, this is not going to fall apart because of these things. Now, if you remove these things, it's going to fly apart. And if it wasn't true right here, then it would come together too hard. But this is perfect. They got just enough pushing away and just enough pulling together that you maintain that structure. That's beautiful. There's nothing like water does that. And if you put ice in alcohol, will ice float or will it sink? Ice will sink in alcohol because I'm not doing this. Alcohol will sink. Yes.
Why doesn't alcohol freeze? Like if you put like your liquid water and you're freezing it.
Because of the bonds.
later and still-
Because it doesn't have the kind of bonding this does.
Yeah, but once you open it and stuff, it automatically will turn to ice. Well, it'll like shoot out and.
But that's not turning to ice though.
It's
If
more like
you shake a
slushy.
Coke and open it, what's going to happen?
It's gonna soak.
That's just carbonation doing that. But in fact, I recall one day where was that? I was in school, I was a student, and the professor walked in and had 2 glasses. And he said, this is like water to me. And he took ice, dropped in one, and it floated. Dropped in one, and it sunk. He said, talk about it. It's way to run. And obviously, they weren't the same liquids, right?
Mhm.
And but the problem was, I'm not a drinker. I didn't know about alcohol not floating ice. By now, I watch TV, and I watch those comedians on stage. You know Ron White, the comedian? That ice is sunk. He's really drinking.
He's always drinking.
But on some movies where you see them, what's supposed to be wine, like whiskey, the ice exploded.
It's tea.
And I know that, that's just water, colored water. But we sat there, and a friend of mine, who's my fraternity, he went and said, I think that's alcohol. And we could talk to each other. And I said, what? I said, because the ice is not floating. And he says, yeah, and alcohol, ice will not float. So we said, we couldn't taste it. We said, from what we know, the physical properties of water, the ice is less dense than water. Water gets under and holds the ice up, the ice floats. But on the same token, alcohol is less dense and the ice will sink in it. He said that you're exactly right. This one's alcohol. He poured both of them out. I think it's rubbing alcohol, not the kind of drink. And that's why he wouldn't let us taste it. I didn't want to anyway, but clearly this arrangement in water is what holds the ice up. That's not an alcohol, ice sinks.
So what, when you have the ice cubes, which is still frozen water.
Correct. But what happens when it freezes, these charges, they get a little further out.
Mm-hmm.
So that it's like a piece of cork in water. Cork has more air inside it, but so does ice. You can see the air in ice.
Okay.
You ever seen how it looks inside the little crystal structure?
Mm-hmm.
And that's also why ice freezes from the outside down. And I've never lived up north long enough to watch a lake freeze. But I know in the hard winter time, you drive across the lake, there's fish still under it from the ground.
Mm-hmm.
They drill holes to the water and they fish to the holes. To me, I don't like fishing that much. But the fact that water freezes like that is another gift of water. If it froze from the bottom up and then became solid, you lose all those fish. I was reading the internet about my goldfish, and one thing about how to humanely kill goldfish. I went, what kind of goldfish? I read about it. They said freeze. The one guy thought he froze goldfish, he would thaw back out and he would live again. Not like, cryogenics. No, if you freeze that sucker, he's dead. I mean, when he thaw back out, he's still belly up. But apparently, if that's the way. They don't say, what they don't do is flush that commode. Then it gets into waterways. Next thing you know, you have some foreign fish out there competing with domestic fish. And that's how we got fire ants over here. But fire ants came in. Oh, killer bees?
Mm-hmm.
They were brought over to South America for an experiment and they got away.
Africa,
And now they're everywhere. But those 11 molecules, and as you see, they're all attached somehow. But they're all also trying to fly apart somehow. That gives a nice, good structure.
Mr. Pat,
Yes.
when you're talking about the fish in the commode, wouldn't, if you flush the fish in the commode and stuff, if it was alive, wouldn't it just go through the sewer system and die? Because
You would think it would.
Fish.
Not necessarily. If the pipes outside my house are dry, it might lay right there and die for being out of water. I don't know. But I do know they say don't flush things because they can get in the sewer system. Now, there's nothing new here. Everything you read there should make perfect sense to you about water. The more you get about water, it gets to be simpler and simpler. When you first start, it seems complex. But when you start looking at the way the bonds work, you go, that's pretty simple, really. Van der Waals forces are fairly simple to comprehend once you get a hang of them. And everything on there is physics. Opposites attract, sames repel. Tell you again about the oxygen being negative, the hydrogen being positive. Everything on there, there's nothing new. I want it to sink in. And I think maybe it's starting to sink in some. The next slide. I'll show it to you again. Now, you've seen that you have the same
Number
charge. Huh?
We didn't get number 6.
Same picture.
No, the
No.
six.
Number 6.
Some people
Yeah.
Oh, okay. And I think I had a picture of her twice. Yeah, I don't need both of those. I'm taking that one off. Let me go back up here where I was. Yeah, this is one. Because it clicked twice, I haven't noticed it. Y'all didn't probably. And everything I've said there, 3 words can describe it. Van der Waals forces. 4 words. That means that's all there is to it. And you may have heard of Van der Waals before, and never knew what it was. It was simply the attraction and the repulsion of water molecules, making them bond in a nice cohesive unit. Y'all do this slide in? That's my picture again. It was there, and I figured I'd just show it to you again as I moved on down through here. And there's number 8.
Where's 7?
I need 7.
I think 7's the picture, right?
Oh, that's it. I think I got this 7 by mistake. Let me come back and all the Z. Under it? Oh yeah, there it is. Something's under it. Okay. I didn't know something was under it. 6. Huh. So when I click it, there's 6. So I'll show you 7. When I click it, there's 7. It lies under my picture. I forgot I did that. I tried to fix it on one book. Always a problem. And this is the flip side. There's nothing, no secrets here at all about how things of the same charges, they dislike each other and they push apart. And where it says clumping together, that's like crushing, and they can't clump because they're being pushed apart. Like I said, if I grab one arm and we had and I pull, we wouldn't come together, would we? Until we move that arm, they're going to smash together then. So this holds us perfectly in line. And this is the pushing. The previous slide was the pulling. The hydrogen bonds would tend to pull the water together. But the opposing bonds say, no, you can't get together. We're going to push you apart. So instead, it just locks everything down perfectly. And all this, when I say to you, Van der Waals forces, that's that pushing and pulling we've been talking all about. That guy's name is this whole concept. Now this is something that I'm throwing a new wrinkle at you on the last half of the slide about the bonds being weaker. I may have told you that, I'm not sure.
It seems like if they were engaging in the hydrogen bonding, then
Seems like what?
it seems like if they're going to engage in the hydrogen bonding, then you wouldn't actually ever get the covalent bonding, which makes up the actual water. Am I wrong?
Well, the covalent bond, you keep the water molecules from flying apart. If you separate water, you don't separate water molecules. You separate this molecule, you just separate molecules. I don't go inside there and break up the hydrogens. Those always get together. But all I'm going to do is just separate where these two are. I can separate the two molecules. I don't go in there and break up these three things. They always get together because these are covalent bonds. But when they come together, and my finger, which is a hydrogen, is drawn to this one. But they can't smash because these are still opposing to one another. I got other waters over here keeping things apart. So when this finger and this thumb, this is hydrogen and oxygen, this is trying to come together. But at the same token, this is keeping them apart. Now, hydrogen, there are three kinds of bonds in this world. Actually, four, but I want to discuss metallic right now. Metallic something else. But the three bonds in living forms, from weakest to strongest. The weakest is hydrogen bonds. The next strongest is ionic bonds, and the strongest are covalent. Covalent bond is the strongest bond we put up with. The weakest bond is hydrogen, and somewhere in there you'll find ionic bond for you. So if you got three compounds, one's ionically bonded, one is covalently bonded, and one's hydrogen bond, which one can you break apart easiest?
The hydrogen
Bond. That's why water is in reaction. Water allows something to be separated and get into the reaction and make things happen. If water was covalent bonded, it wouldn't get into reaction. Again, you're still talking about those hydrogen bonds between the H and the O. That's the beauty of water, those hydrogen bonds. Now I know in one water molecule, this is covalent bonds, so these together, covalent bonds. And this water molecule, covalent bonds. But to make these two stick together, right there, hydrogen, that's hydrogen bonds. If I'm going to separate them, I ain't going to separate here. I'm going to separate two molecules. And then what gets inside there might be sodium or chlorine or some other reactant to make a reaction go. Can you cook without using water? Think about it. Can you cook a meal with no water?
Steam.
But even when I cook hot dogs, I put them in water. I bake a cake. What do you put in flour? Water. Well, I use milk. Well, guess what milk is? Water. Just because you camouflage it don't mean it ain't water. And when you drink a meal, you drink milk or wine or Coke or you getting water in there to make the reactions go. To break down that meal you've eaten. If you can't break it down, what's good of eating? You're going to die of starvation if you can't break it down. So that slide just, the whole thing is about hydrogen bonds. The next slide, let's see what we got. Now, I've got 4 things on here, A, B, C, and D, which talk about the goodness of hydrogen bonds. And I try to change colors in my text. Well, I change from A to B to C to D. A is in kind of a reddish color, and B is black, and C is kind of that bluish looking color, and D is back to black. We're trying to make it easier to read. I've discussed A. I didn't mention B to you. I didn't mention C to you. I've kind of mentioned D before. I need to hear him again though, probably. Now, are you too complicated if I talk? I'm going to talk to you soon. I don't want to mess up your thinking or your talking.
Yes, ma'am. Okay.
Let's talk about A first, about floating water. I got O repelling O, right? I got H loving O, right? All right. This is the weakest bond there is. the repulsion of these two electromagnetics is real strong. When you freeze water, you weaken that hydrogen bond, and that makes these things shove further apart. If you have lost you now. Think about that. There's your hydrogen bond that's making them stay together. These bonds are stopping them from flying together. Now, when I freeze it, if I weaken that bond, won't the repulsion go further apart? Well, when they go further apart, they get more distance between them. So if you compare this of ice to this of water, this one has more air inside it. It will float like cork. So ice with the wider structure is like a block of wood in Lake Oliver. The wood being less dense will float on the water. Well, so will ice. Ice will float because it too is less dense. But in that case, though, temperature doesn't. Now, when you thaw the ice, it will turn back. You can't ever have ice that's going to sink in water because by then it's turned back to water. If you heat the ice, it gets an iceberg, for example, is extremely cold and it is salt, so you can freeze salt. But where's most of the iceberg? Above and below the water. Ask the Titanic. He'll tell you where it is. They never saw the ice he did. Well, even your own glass of iced tea, most ice is under the surface of the tea. Just a little bit is broken surface. And if you froze it harder, but you can't freeze it harder. At 32, it stopped. That's it. Or at 0, you can't make ice colder than ice is. Now I can. Now water, I can make it be 33 degrees. I can make it be 99 degrees. Now at 100 degrees, it becomes steam, right? So I lose my water. And at 32 degrees, it becomes ice. I lose my water. Water is that liquid stuff. Solid water is the ice. Liquid, the gaseous water is the steam. You ever seen your pan start? You got your pan on your stove. You're going to make some deviled eggs. You boil them, right? And you turn the heat on. You ever notice that first big blast of water, boom, comes up from the bottom? Right there on the bottom of that pan, an air bubble is forming as where it's touching the pan is real hot, right? Right there, that water is turning to gas on the bubble, but not being able to get it to break free. And all boiling water is, you'll see where the bottom here, you'll form the gas bubble. It will come to the surface and burst. That's your boiling water. And as it bursts, it's letting go water vapor. Can you boil water away and turn your pan up? Well, you know you can. And it's easy for you ever cook oatmeal to a brick because you've got it on the stove. How thick your oatmeal is depends on how long you boil it, right? If you like soupy oatmeal, do you boil it long or short? Short. If I like it a little thicker, then I boil it. But you better watch it though. You better stir it. But if you stick the bottom of the pan, the oatmeal is almost like concrete. If it's solid, you throw the pan with you, new one. Alright. But it's those bonds that make ice actually float in the water. Alcohol doesn't have, and the ice won't float in alcohol, it will sink to the bottom of alcohol. The next one here, those bonds let water be liquid from 32 degrees, 34, 35, 36, 95. At 100 though, it turns to gas. Is that gas hot? You better believe it's hot because that's 100 degrees. Will steam burn you?
Yeah.
In a heartbeat. Put your hand over boiling water, try to turn the water off and roast your. We steam vegetables all the time. Mm-hmm. Steam is a good way to cook food. It'll also cook your arm if you're not careful. But the bonds allows that water to be a liquid. I mean, If on this earth water had a different point, and say the water froze at 60 degrees, how long would life last on earth? At 60 degrees? Can't, if you're in the Arctic and when there's ice, any water to drink? Any water to drink? If you lick it, your stomach takes to it. All you can do maybe is try to hold it by your body and warm it up to turn. I mean, you're out there in a raft in the ocean floating around. You know what I'm saying? Water everywhere. And not a drop to drink. You'll die right there in the ocean. Water everywhere. But you can't drink salt water. Fish live in the ocean can do. Because they have modifications. I mean, what's amazing, would you go out in the woods and find the mushrooms and eat it?
No.
Deer do. If I'm deer hunting, if I find mushrooms, I stop. Deer love mushrooms. And I know I wouldn't know what that mushroom he just ate. Deer have enzymes inside them that make that hormone, that make the enzyme that would kill us, not kill him at all. You still have vultures eat?
Anything else?
Would you eat what a vulture eats?
No.
It would kill you. But that bird has a whole different system inside him. His metabolism makes it possible. He's that dead roadkill, been there for a week, stinking. You think I'd eat that sucker? No. I'm glad we got buzzards though. I want it gone. Don't want to lay there ever. And that buzzard has, since lost your buzzard up, right? You can't just shoot one? Well, you can, but like in our history, you be in jail. Since lost that. That's how we get things back in nature. Buzzards decompose it like bacteria do. Yeah.
Just let me know it's 1:45.
Huh?
It's 1:45.
Oh, good. Let's stop. Let me see where we're at.
10.
Good.